In the summer of 2012, a financial services firm called Knight Capital Group deployed this new piece of software to their servers.
Oh, man. I know exactly where this is going.
Right. It is just the ultimate nightmare scenario. They were getting ready for a new retail liquidity program on the New York Stock Exchange.
Yeah.
And when the market opened at 9:30 a.m., their computers just automatically started buying and selling stocks like they were supposed to. But there was a flaw.
A massive flaw.
Exactly. A dormant piece of code, something that, was supposed to have been completely deleted, was accidentally activated because literally one single server out of 8 hadn't been updated properly.
Just one server. That's all it takes.
One server. And in the first 45 minutes of trading, that software bug bought and sold millions of shares it wasn't supposed to touch.
It's just staggering to think about.
It cost the company $440 million.
Wow.
$10 million a minute. Completely vaporized. All because of one untested deployment.
It really remains, one of the most terrifying cautionary tales in modern software engineering. It perfectly illustrates the sheer scale of the blast radius when code interacts with the real world.
Absolutely.
Right.
And that's why we're here today. Welcome to the Deep Dive. We are so thrilled to have you here with us. You're the kind of learner who doesn't just want to, casually use technology. You want to look under the hood.
You want to know how the engine actually works.
Right. You want to understand the invisible systems running our world without drowning in all that dense technical jargon. And today, we are exploring a massive paradigm shift.
But a really fundamental shift.
Yeah, because back in 2012, to create a catastrophic software failure like Knight Capital did, you had to be a highly trained engineer working at a massive, sophisticated firm.
You had to have access.
Exactly. But today, thanks to generative AI, literally anyone with an internet connection can conjure up a fully functional application just by typing a sentence into a text box.
Which is amazing, but also terrifying.
Right. We are handing out loaded weapons to millions of people without teaching anyone where the safety switch is.
That's a great way to put it. The barrier to creation has completely evaporated. It's gone. But the barrier to quality, the actual requirement for safety, reliability, and precision, that has never been higher.
Because the stakes are so high now.
Exactly. If anyone can build an application that scales to thousands of users overnight, well, anyone can build a bug that causes a massive real-world disruption overnight.
And that brings us to our mission for this deep dive. We're taking two entirely different disciplines that we have source material for today. On one side, we have the highly rigorous world of traditional software testing, and on the other, this brand new sort of Wild West frontier of AI prompting.
They seem totally unrelated at first glance.
They really do.
Yeah.
But we're going to show you how they are actually the exact same discipline.
Two sides of the same coin.
Yeah. They are both fundamentally about control. How do we guarantee the machine does exactly what we want, and how do we mathematically prove that it actually works?
Okay, let's unpack this. Because to understand how to control the machines of the future, we first have to really grasp the guardrails that the software industry has spent, the last 40 years building?
Yeah, at least 40 years.
You're right. And that overarching guardrail is called the Software Development Lifecycle, or the SDLC.
The SDLC. And let's try to avoid the whole cliche of comparing software development to building a house.
Please, it never quite fits.
If it doesn't. Because a house is static. You build it, and it sits there. Software is alive, it's constantly moving, it's updating, it's interacting with totally unpredictable users.
It's much more like orchestrating a global supply chain.
Yes, exactly, a supply chain. You don't just start building factories blindly and hope for the best. The life cycle begins with planning and requirement gathering.
Right.
This is essentially your market research phase. What are we actually building? Who is it for? And what specific problem does it solve in the world?
And that is followed immediately by analysis and designing, which, if we stick to your supply chain analogy,
Yeah, let's do it.
this is where you map out the shipping routes. You design the warehouse layouts. In software, you are designing the architecture, the databases, the user interface workflows.
You're figuring things out before you build.
Exactly. You are answering the how before anyone even picks up a tool or writes a single line of code.
And then comes implementation, the actual coding phase.
The manufacturing.
Right, the manufacturing phase, where developers sit down and write the logic. And I want to pause here because this is exactly where the generative AI revolution has completely inverted the traditional model.
It really has turned it upside down.
Because traditionally, implementation was the biggest bottleneck. You needed a team of senior engineers writing code for months, sometimes years.
Just typing away.
Yeah, but now, an AI model can spit out the foundational code for a web application in about, what, 14 seconds?
Sometimes less. The manufacturing phase has effectively been commoditized.
Which logically forces that bottleneck further down the pipeline. If manufacturing is basically instant now, the most critical phase of the entire life cycle becomes the fourth step.
Yeah.
Testing.
QA at the border.
Exactly. Checking the software for errors, bugs, security vulnerabilities, and logic flaws before it ever moves to deployment, which is, releasing it to the public, and then maintenance.
What's fascinating here is that because AI allows anyone to generate code, software testing is no longer just this specialized niche IT job for quality assurance engineers.
It's for everyone.
It is a foundational literacy. If you are going to use AI to build something, you absolutely must possess the vocabulary and the frameworks to test what it builds for you. You can't just trust it blindly.
But if AI is doing the heavy lifting of writing the code for us now, aren't we just, inspecting the AI's work? Does the traditional SDLC still apply?
Oh, it applies more than ever. The software industry actually has a very specific framework for this inspection process. It's called the pyramid of testing.
The pyramid of testing.
Yeah, it's a structure designed to build trust systematically. You move from a broad foundational base all the way up to a narrow peak. And let's start at the very bottom of that pyramid, which is unit testing.
Unit testing. So what does that actually look like on the ground?
Unit testing operates at the most granular level possible. You are testing the smallest compilable piece of code in total isolation.
So no database is connected, no user interface.
Right. You aren't loading up the server. You are taking one single function, feeding it a very specific input, and mathematically verifying that it produces the exact expected output.
Okay, let's make that concrete for a second. Imagine you ask an AI to build a really simple React application, something super basic. Let's say just a web page with a counter in the middle.
Oh, okay.
And there's a button that says increment and a button that says decrement. It seems incredibly basic. But how does a developer actually write code to test that code?
Well, they use a testing framework, something like the React testing library. The framework provides specific tools to simulate the browser environment without ever actually opening a web browser.
Oh, interesting.
Yeah, it's all in the background. First, the test uses a command called render, and this takes your tiny counter component and essentially draws it into an invisible virtual sandbox in the computer's memory.
Okay, so it's basically staging the environment, like a rehearsal.
Exactly like a rehearsal. Then, the test uses a command called screen to search that invisible sandbox for specific elements. It scans the virtual page looking for, say, a button with the text increment.
Right.
Once it finds it, we use a command called fire event, and this is the crucial part. The code fireEvent.click artificially simulates a human mouse click on that specific button.
That's wild. So it's a phantom click, and then the test obviously has to verify the click actually did anything, right?
Yeah.
Right, it has to make an assertion. It uses a command like expect to have text content. So the code literally reads like a sentence. It states, after I fire the click event, I expect the text inside the counter display to change from 0 to 1.
And if it works?
If the virtual display reads 1, the test passes. A tiny green check mark appears in the developer's terminal.
And if it doesn't? Like, what if the developer messed up the math?
Then the display might read 0, or maybe even NaN, which stands for not a number. In that case, the test fails. It flashes red. The beauty of this is the determinism. The developer knows instantly, within milliseconds, that the specific logic for that single button is mathematically sound.
That makes total sense. Let's apply that to something slightly more complex, like a to-do list application. We all use these every single day. You type, buy groceries, hit enter, and it adds it to a list. But the unit tests for a to-do app really reveal how deeply developers have to anticipate human unpredictability. Because you don't just test the happy path, which is what happens when things go perfectly right. You have to write preventative tests for when users do bizarre things.
Oh, absolutely. Because users will always do bizarre things. That is a guarantee.
Right. So what happens if a user clicks the input box, types absolutely nothing, and violently clicks the add button 10 times in a row?
If the developer hasn't accounted for that, the application might try to send 10 empty text strings to the database. And the database might throw an error, panic, and crash the entire application for everyone.
Just from clicking an empty box.
Yes. So the unit test explicitly checks the empty state. It simulates clicking add with an empty input and asserts that the array of tasks remains totally unchanged. It tests sequence, too. Like, if I add 3 items, do they index correctly?
1, 2, 3.
Right. And if I delete the middle item, does the array collapse properly, or does it leave this terrifying null void that breaks the whole visual layout?
A null void sounds like a sci-fi movie. But these tests, they're written right alongside the application code, right?
Correct. They live together.
And the barrier to learning how to write these tests is lower than ever. You don't even need to configure a massive local development server on your laptop anymore.
No, not at all.
There are cloud-based IDEs integrated development environments like Code Sandbox for JavaScript or Google Colab if you're using Python. They give you a fully configured environment running right in your web browser where you can practice writing these unit tests immediately.
It's incredibly accessible now.
Okay, so we have thousands of these tiny microscopic unit tests running in milliseconds, and they form the massive base of our pyramid. But eventually, a button has to actually talk to a database, right? The isolated pieces have to connect to each other.
And that introduces the middle layer of the pyramid, integration testing. This is where you verify the handshakes between different services.
The handshakes.
Yeah. For example, if your to-do app relies on an external weather API to tell you if it's going to rain today, the integration test ensures that when your app requests data, the external API actually responds. And more importantly, that your app understands the specific JSON data format it receives back.
Okay, so it's testing the communication lines.
Exactly. And then above that, we reach the very peak of the pyramid, end-to-end testing, or E2E.
E2E. I've also heard some engineers call this UI testing or automated browser testing.
Yeah, they're generally referring to the same thing. This is the heavyweight division. You are spinning up the entire application, the front-end interface, the back-end servers, the real databases, and you're simulating a full, complex user workflow from start to finish.
Real user action.
Real actions. E2E tests provide the ultimate level of confidence because they replicate reality. You are proving that the entire system works in harmony, but they are incredibly resource-intensive.
They're heavy.
Very heavy. They take a long time to run, and they are notoriously prone to environmental flakiness.
Let's pause on that word flakiness, because there is a trap here that I know a lot of novice developers fall into. If an end-to-end test perfectly simulates the real user experience and it gives us the absolute highest confidence, why do we even bother writing thousands of tedious unit tests?
It's a fair question.
Why not just build a robot that clicks through the app and call it a day? Skip the base of the pyramid entirely.
If you rely entirely on end-to-end tests, you are building a system that tells you that you are failing but completely refuses to tell you why.
Oh.
Imagine you are running Amazon. You write an end-to-end test that simulates a user logging in, searching for a laptop, adding it to the cart, and checking out. You run the test, and a massive red error pops up on your screen. Checkout failed.
Oh, okay, so what broke?
You have absolutely no idea.
Wow.
Did the search indexing microservice fail? Did the add to cart state management drop the data? Did the third-party credit card gateway timeout? Did the state tax calculation function accidentally divide by 0?
You're just blind to the cause?
Completely blind. It's like having a check engine light on your dashboard. It alerts you to danger, sure, but you still have to tear the entire engine apart to find the single frayed wire. Debugging a broken E2E test without underlying unit tests can take days.
That sounds miserable. But if you have the full pyramid of testing in place, the E2E test fails, and simultaneously, a tiny unit test way down at the base of the pyramid flashes red and says, hey, the tax calculation function for zip codes in New York is returning a null value.
Exactly. You bypass the entire investigation phase. You know exactly which line of code is broken instantly.
That is brilliant.
And furthermore, the sources mention there are several other specialized types of testing that run alongside this main pyramid.
Right.
Performance testing is critical. You can't just assume your app will work when it scales to millions of users. Engineers use tools to artificially generate thousands of virtual users, pinging the server simultaneously to see where the memory leaks are, or, at what point the server literally catches fire.
And there's regression testing, which I actually find fascinating from a mathematical perspective. Every single time a developer adds a new feature to the codebase, they run the entire historical suite of tests to mathematically prove that the new code didn't inadvertently break an old, completely unrelated feature.
Which happens all the time.
All the time.
There's also accessibility testing, ensuring that screen readers and navigation tools for users with disabilities can actually interpret the application's DOM, the document object model. Security testing to hunt for vulnerabilities like SQL injections. And, of course, traditional manual testing.
Where a human just clicks around trying to break things.
Yep, the old-fashioned way.
But humans are slow. Humans get tired. We miss subtle visual changes on the screen. If a tech company deploys new code to production 50 times a day, they cannot rely on a human manually clicking through the site 50 times a day to make sure checkout works. We have to automate the human.
We have to build robots.
Yes. And this brings us to the two heavyweight automation frameworks dominating the industry right now that are detailed in our sources: Cypress and Selenium.
These frameworks are essentially tools for building those robots that perform our end-to-end tests. Let's look at Cypress first, because it represents a major architectural shift in how we test the web today.
Okay.
Cypress is a JavaScript-based framework, and its defining characteristic, the thing that makes it special, is that it operates directly inside the modern browser.
Wait, what does that actually mean? Mechanically, how is it inside the browser?
Good question. So, most traditional testing tools send commands to the browser over a network protocol. They act as an external force telling the browser what to do.
Like remote control.
Exactly. Cypress, however, actually injects its testing code directly into the same event loop that your application is running on. It has native, synchronous access to the document object model, to your application's memory, and even the network layer. It isn't guessing what the browser is doing from afar. It knows exactly what the browser is doing because it is effectively part of the browser's brain.
That deep integration. That actually gives Cypress a feature that solves one of the biggest headaches in automated testing, doesn't it? Waiting.
Waiting. Flakiness due to timing issues is the absolute bane of an automation engineer's existence.
Right.
Imagine your test clicks a submit button and then is programmed to immediately check if the green success message appears on the screen. But your network is slightly slow today, so the page takes, say, half a second longer to load.
Just a tiny delay.
Just a tiny delay. But the test looks for the message, doesn't see it instantly, and violently fails the entire build. It reports a critical bug that doesn't actually exist. It's a false positive.
And the old solution to that was terrible. You had a hard-coded command telling the test to simply sleep. Like, click the button, completely freeze for 3 seconds, then check for the message.
Which works, but
if you have thousands of tests, and you're adding artificial 3-second waits to all of them, suddenly your test suite takes 4 hours to run.
Cypress completely eliminates this. Because it's inside the browser, it has automatic waiting. It monitors the DOM natively. It knows when an element finally becomes visible. It knows when a CSS animation finishes.
Yeah.
It knows when a network request is still pending.
It has total awareness.
Exactly. So it automatically pauses its assertions until the application reaches the desired state. It makes the test incredibly fast and highly deterministic. You don't have to guess how long to wait.
Our sources also mention it has a feature called time travel debugging, which sounds like a game changer for developer experience.
Yeah.
When Cypress runs a test, it literally takes a DOM snapshot at every single command it executes.
Yes.
So if a test fails on step 42, the developer doesn't have to just guess what went wrong or read a cryptic error log. They can literally hover their mouse over step 41, step 40, step 39, and watch the visual state of the application rewind like a videotape. They can see exactly what the screen looked like at the exact millisecond the error occurred.
It's brilliant. It also allows for network stubbing. Well, because it sits inside the browser, it can intercept outbound API calls. So if you are writing a test for a checkout flow, you obviously don't want your test to actually hit the real Stripe API and charge a real credit card every single time the test runs.
That would get expensive fast.
Very expensive. Cypress can intercept that request as it's leaving the browser, block it, and feed the application a fake success response so the rest of the UI test can continue without spending any real money.
So Cypress is incredibly fast, it's developer-friendly, and it's highly stable. But it does have a ceiling. It only runs on modern browsers, primarily Chromium-based ones, and Firefox. It is strictly tied to JavaScript. And it does not natively support complex flows that require opening multiple different browsers simultaneously or, interacting with multiple tabs at once.
Right. If you are a massive enterprise bank and you need to mathematically guarantee that your software works flawlessly on a 10-year-old version of Safari running on an old iPad, Cypress is simply not the tool for the job.
Which brings us to the industry titan, Selenium.
The heavyweight.
Selenium is an open-source automation framework that has basically been the backbone of enterprise testing for over a decade. It is designed for massive scale and absolute cross-browser compatibility.
And unlike Cypress, Selenium operates outside the browser. Let's break down its architecture because it really is a brilliant piece of engineering.
Let's do it.
It consists of 3 distinct layers. First, there is the code that you write, which utilizes the WebDriver API. And the beauty of Selenium is that you aren't restricted to JavaScript like you are with Cypress.
You have options.
Tons of options. You can write your tests in Python, Java, C#, Ruby, literally whatever language your backend team is already comfortable using.
Okay, so that's layer one.
Right. That code sends commands to the middle layer, which is called the driver. For example, Chrome driver if you're using Google Chrome, or Gecko driver for Firefox. The driver is an actual executable file, a physical piece of software that runs on your local machine.
Right.
It acts as a translator. It receives the high-level commands from your Python script, translates them into the highly specific native instructions that the browser understands, and then physically derives the browser to execute them.
You know, I think of it like this. If Cypress is like giving a car a self-driving brain, where it's wired directly into the engine, the transmission, the sensors, and it feels the road natively.
Yeah.
Selenium is like building a complex robot, sitting it in the driver's seat of a regular car, and giving it a walkie-talkie.
Oh, I love that analogy.
You stand on the sidewalk and shout instructions over the radio, push the accelerator, turn the wheel left. The robot physically pushes the pedals, but it doesn't inherently feel the engine. It's just following external orders.
That is exactly the dynamic. And because Selenium is outside the car shouting instructions, it requires explicit waits. Unlike Cypress, it doesn't automatically know when the page is loaded. You have to program the logic to tell the robot, clicks the button, now continuously pull the page every half second until the specific element ID appears, and only then proceed. You have to manage all that synchronization manually.
And the setup process for Selenium is also much more manual, isn't it? You don't just download an app, click run, and start testing.
Oh, no. It can be quite a hurdle. If you are using Python, you have to open your computer's command terminal. You use pip, which is Python's package installer, to reach out to the internet and download the Selenium libraries.
Okay.
Then you have to download the specific driver executable that matches your exact browser. And this is what trips up almost every single beginner.
How so?
If you have Google Chrome version 1.15 installed on your machine, you absolutely must download Chrome driver version 1.15. If Chrome silently auto-updates in the background overnight to version 1.16,
Which it always does,
your entire test suite will suddenly crash the next morning because the versions don't match anymore. The walkie-talkie doesn't speak the same language.
And you can't just put that downloaded driver anywhere on your computer, right? You have to place it in a directory that is explicitly listed in your system's path variable.
Let's actually explain that, because it's a concept from the source material that confuses a lot of non-developers. Your operating system, whether it's Windows or Mac OS, has a hidden internal map called the path variable.
A hidden map.
Yeah, it's essentially a list of specific folders. When you type a command into your terminal, the computer only searches the folders listed on that map to find the program you want to run.
Got it.
So if you put the Chrome driver executable in some random folder on your desktop and that desktop folder isn't on the map, your Python script is essentially blind to it. It will throw a fatal error saying executable needs to be in path.
But once you navigate that setup, the power you have is staggering. You are essentially a digital god commanding the web. Think about a project like building an Amazon automation bot.
Oh yeah, that's a classic Selenium project.
You write a Python script that instantiates the web driver. It commands the browser to open Amazon.com. It uses locators like XPath, which is a specific syntax for navigating the XML structure of a web page, to perfectly target the search bar.
It types laptops, hits enter, it waits for the page to load.
And then it loops through the search results, scraping the price, the specifications, the reviews, and dumping all that data into a neat Excel spreadsheet. You have programmed a robot to do your rigorous market research while you sleep.
It's an incredible feeling of leverage. You feel like you have superpowers.
But this is exactly where our two disciplines collide today. We have spent all this time establishing how developers use code to test software. But as we established at the very beginning of the deep dive, the developer isn't writing the code anymore.
The generative AI is writing the code.
Exactly. You can ask an AI to write the React application, and then you can ask the AI to write the complex Selenium test script to verify that the application works.
But here is the massive catch. How do you ensure the AI writes the correct script? If the AI misunderstands what you want, it will generate absolutely flawless, syntactically perfect code that does the completely wrong thing.
And this is the revelation. We used to spend weeks in the requirement gathering phase of the SDLC to make sure our human developers knew exactly what to build. Today, the prompt is the requirement document.
Yes. AI prompting isn't just some parlor trick to make funny poems. It is the new frontier of software engineering. If you can't write a rigorous prompt, you cannot control the machine.
And thankfully, Google has published a robust framework for structuring these natural language requirements. It's essentially a syntax for speaking to models like Gemini or ChatGPT, and it relies on four non-negotiable pillars: persona, task, context, and format.
Let's look at how this actually changes the output. Imagine you need marketing copy for a new washing machine. A novice user will just open the chat and type, "Write a tagline for a washing machine."
And the AI will output something incredibly generic like, wash your clothes well. It's totally useless.
Completely useless. But if we apply the Google framework, we start with the persona. We say, you are a seasoned advertising copywriter.
Let me stop you right there because I've always wondered about this specific point.
Yeah.
Is assigning a persona just a fun psychological role-play trick we play on ourselves? Or does telling the AI to act like a copywriter actually change the mechanical way the computer processes the request?
That's a brilliant question. It fundamentally changes the math inside the neural network.
Really? How?
Large language models operate on what we call vector spaces. They map relationships between words as coordinates in a massive multidimensional mathematical space. When you type, "You are a seasoned advertising copywriter," you are mathematically activating a specific cluster of weights and biases within the model's neural network.
Oh, wow.
You are telling the attention mechanism to prioritize the statistical patterns found in the marketing textbooks, ad copy, and behavioral psychology data it was trained on. And simultaneously, you are telling it to suppress the vocabulary of, say, Wikipedia articles or Reddit forums. You are narrowing the probability tree.
That makes so much sense. You are calibrating the instrument before you take the measurement.
Exactly. Okay, so the next pillar is the task. It needs to be direct and action-oriented. Create a concise tagline.
Then comes the context, the boundaries of reality. The washing machine gets clothes extra clean, has 25 customizable settings, and fits in a small space.
Which is vital, because
Yeah.
without this context, the AI hallucinates. It might write a brilliant poetic tagline about how eco-friendly the machine is, which is totally useless if your specific machine actually uses a ton of water.
And finally, the format, the structural constraint. The tagline should use an active voice and be no more than 6 words. If you leave out the format, the AI might give you a 3-paragraph essay when you just wanted a slogan.
Right, so when you combine them all together, you are a seasoned advertising copywriter. Create a concise tagline for a washing machine that has 25 settings and fits in a small space. The tagline must use an active voice and be no more than 6 words.
You have provided a perfect requirement document. The AI produces a highly targeted, usable asset.
Google actually expands on this discipline with what they call the 3 C's of prompting.
The 3 C's.
Yeah, the first 2 are fairly intuitive. Be concise and be clear. Don't write a meandering novel for a prompt, and avoid subjective, vague words like "make this better." Give precise parameters.
But the third C is where things get highly technical, right? Be consistent.
Be consistent.
The example they provide in the source is absolutely fascinating. They explicitly warn that if you start your prompt by asking the AI to populate a spreadsheet, you must religiously use the word spreadsheet for the rest of the conversation.
Do not deviate.
Right. If you casually switch to calling it a matrix or a data tab in your follow-up prompts, the AI actually gets confused and the output degrades. Why is that?
Yeah.
Because as a human, if I say spreadsheet and then 2 minutes later refer to the matrix of numbers, you know exactly what I'm talking about. We have contextual intuition.
But the AI does not have intuition. It has probability. As a predictive text engine, it is constantly calculating the mathematical likelihood of the next token, or word fragment, based on the entire sequence of words that preceded it.
Right.
The word spreadsheet is strongly correlated with a specific mathematical cluster: Microsoft Excel, rows, columns, financial data. The word matrix, on the other hand, is correlated with a totally different cluster: linear algebra, complex arrays, or, science fiction movies.
So by swapping a single synonym, I am gently pushing the steering wheel of the AI into a different lane.
Exactly. We call it context drift. Over the course of a long conversation, if you are inconsistent with your vocabulary, the mathematical weights become diluted. The AI loses the plot because you essentially muddied the vector space. Consistency is how you keep the model locked onto your specific domain.
That level of precision is exactly how developers treat code, which leads to one of the most powerful concepts in the Google Guide, the prompt library.
Yes, the library.
When you spend 20 minutes refining a prompt, testing the vocabulary, and getting a spectacular output, you do not just close the tab and forget about it. You extract the core structure, replace the specific details with variable brackets, and save it as a template.
So it looks something like, help me with a task.
Yeah.
Use the expertise of persona. The output should be format, context, context.
It's literally a reusable software function. In traditional software, you don't write the raw code for a login system every single time you build a new app. You write a function called authenticate user, you verify it works, and you call it whenever you need it.
Yep.
By building a prompt library, you are creating a repository of pre-tested, high-functioning linguistic code that you and your team can call on demand. You are scaling your communication.
But just like scaling code, scaling prompts requires rigorous QA. You cannot blindly trust the output, even from a good template. The guide dedicates significant space to evaluation and iteration. You must evaluate the AI's response against 4 specific criteria: accuracy, bias, relevancy, and consistency.
Accuracy is obvious. Did it hallucinate?
Mm.
The AI might confidently invent a Python library that doesn't actually exist because the statistical probability of the words looked correct.
That happens a lot. And bias is a mechanical reality of the training data. If an AI is trained on historical internet text, and that text contains societal or historical skews, the model's probability engine will naturally reproduce that skew. It's not malice, it's a data integrity bug.
And relevancy asks if it actually adhered to your constraints. Consistency checks if the tone remains stable throughout the output. If the output fails any of these criteria, you don't just throw your hands up and say AI is useless.
Yeah.
You iterate. You debug the prompt.
And the guide offers incredibly specific iteration techniques. One of the best is to break up complex tasks. Instead of asking the AI to do a massive calculation and apply it to your life in one massive paragraph, you split it.
So step 1, explain the key principles of effective decision-making.
Right. You evaluate that output first. If it's sound, you proceed to step 2. Now, apply the specific principles to the agenda for my weekly status meeting.
Think about the underlying logic of what you are doing there. Wait, that is unit testing. We are literally unit testing the AI's thought process.
Precisely. We're testing the components. If you asked for the final application all at once and the advice was terrible, you wouldn't know where the bug was. Did it misunderstand the context of your meeting? Or does it possess a fundamentally flawed definition of decision-making?
You wouldn't know.
By forcing it to output its foundational logic first, you are testing the smallest compilable piece of its reasoning. If step 1 is flawed, you correct the definition before allowing it to generate the final end-to-end output. You are actively applying the pyramid of testing to natural language.
That is such a powerful connection. Another iteration technique they mention is adding aggressive constraints. Provide a solution that requires zero budget and can be implemented in 3 days. Constraints force the AI to abandon generic, theoretical fluff and calculate practical applications.
And you can guide that practical application using references. A large language model is essentially a mirror. It reflects the data you show it. If you want a specific tone, don't just use adjectives. Provide a reference block of text.
The guy gives a great example for an indie rocks music festival. Instead of saying, write a cool social media post, the prompt says, write a post promoting a festival. Use the following example as a reference for tone. Where mountains meet music, Indie Rocks Festival returns. Your favorite local bands plus national acts. Hashtag support local music.
By analyzing that reference, the AI maps the cadence, the sentence length, the enthusiasm level, and the hashtag usage. It reverse engineers the style and applies it to your new task perfectly.
But there's a massive trap here. If you are iterating, testing step 1 and step 2, providing references and chatting back and forth, you're filling up the context window. And understanding the context window is probably the single most important technical rule for operating generative AI.
The golden rule is start a new chat for a new topic. Period.
I have to admit, as a user, this feels counterintuitive. It feels tedious. If these AI models are supposedly displaying sparks of general intelligence, why can't they follow a conversation like a normal person? If you and I are debating the architecture of Selenium, and then I suddenly ask you what you want for lunch, you don't stare at me blankly and try to automate a sandwich.
Yay.
You seamlessly switch contexts. Why do I have to wipe the AI's memory just to change the subject?
Because the AI does not experience time or memory the way a human does. Humans have a hippocampus. We compartmentalize information naturally. The AI basically has amnesia. Between every single turn of the conversation, the neural network effectively resets to 0. Its only memory is the transcript of your chat.
Wait, what do you mean by that? How does it reset?
When you type a new prompt at the bottom of a long conversation and hit enter, the AI doesn't just read your new sentence. The system takes the entire history of that specific chat session, every single prompt you wrote, every paragraph it generated in response. It bundles it all together into a massive block of text, converts that text into mathematical tokens, and feeds the entire sequence through the neural networks simultaneously to calculate the probability of the very next word.
So if I've been discussing the Indie Rocks Music Festival for 45 minutes, and we've generated, say, 4,000 words of marketing copy, and then at the very bottom I say, by the way, write a Python script for a to-do list.
The neural network is forced to process 4,000 tokens related to guitars, mountains, and social media, alongside your one sentence about Python. Those 4,000 tokens exert massive mathematical gravity. They dilute the focus of the attention mechanism. The AI might generate your Python script, but it might inexplicably name your variables guitar string and mountain stage because that vocabulary is dominating the probability matrix of the context window.
That is mind-blowing. It's not remembering. It is recalculating the entire history of the universe every time I hit enter.
Exactly. When you click New Chat, you are creating a clean, pristine mathematical environment. You are isolating the variables. Just like a developer ensures a unit test runs in a clean, isolated virtual sandbox so external data doesn't corrupt the result, you must isolate the AI's context window so extraneous tokens don't corrupt the logic.
It really does all come back to control. So let's synthesize this incredible landscape we've mapped out today. We started in the concrete, deterministic reality of the software development lifecycle. We recognize that the implementation phase, the actual writing of code, has been democratized by generative AI. Anyone can build now.
Which means the testing phase is no longer optional. It is the ultimate safeguard against catastrophic deployment failures.
We explored the tools engineers use to build that safeguard. The pyramid of testing, establishing a massive base of fast, localized unit tests to verify the smallest pieces of logic, moving up to integration tests, and finally capping it with end-to-end automated workflows to ensure the entire system functions in reality.
And we looked at how frameworks like Cypress revolutionize this by sitting directly inside the browser's event loop, providing automatic waiting and time travel debugging. And we contrasted that with the sheer power of Selenium, utilizing WebDriver to act as a robotic proxy, driving massive cross-browser test suites from the outside in.
And then we crossed the bridge. We realized that if AI is now writing the code, and AI is writing the Cypress and Selenium test scripts to verify the code, we must control the AI. We do that through the rigorous discipline of prompt engineering.
Treating natural language as a requirement document, defining the persona, the task, the context, and the format, maintaining strict mathematical consistency with our vocabulary.
We learn to evaluate the output, hunting for hallucinations and biases, and to iterate by unit testing the AI's logic step by step before asking for a final product. We learn to manage the context window to prevent mathematical drift. We are applying the exact same rigor, isolation, and verification principles of software engineering to the way we type English sentences into a chat box.
The tools have changed, but the fundamental pursuit of accuracy remains exactly the same.
Which leaves me with a thought that I really want you, the listener, to explore on your own. For decades, we believed that the language of the future was syntax. Python, JavaScript, C++ me. We told everyone to learn to code because the machine only understood semicolons and brackets.
That was the mantra.
But the paradigm is flipped. We now live in an era where the machine understands logic natively. The AI writes the code. The AI writes the test to check the code. The only human element left in the entire loop is the initial instruction. Yes, the intent. Which means the ultimate software bug of the future will not be a missing semicolon in a React component, and it won't be a misconfigured path variable for a Selenium driver. The ultimate bug will be a lack of clarity in human communication. If we cannot articulate exactly what we want with precise constraints and logical context, the machines will flawlessly execute our misunderstandings at scale.
The technology is ready to build whatever we ask of it. The only limitation left is our ability to explain what we want.
Our natural language skills, our ability to use words with precision, empathy, and structural logic, actually becoming the most important programming language on Earth. We want to thank you so much for joining us on this deep dive. We invite you to take these frameworks, the testing pyramids, the prompting templates, and test them out in your own projects. See what happens when you apply the rigor of code to the way you speak. Until next time, remember the magic. You type a sentence into a box, and something new comes into the world. Just make sure you know how to control it.